In the previous section, we compared various FPGA data sharing methods. By the end of this module, you will be able to synchronize FPGA loops using occurrences. So now we're going to start Lesson 9, which is synchronizing FPGA loops and I/O. So first we'll talk about how to synchronize FPGA loops, and in the second half, we'll talk about synchronizing C-Series I/O modules. Okay, so let's talk about synchronizing FPGA loops. So many FPGA applications require synchronization, and you might need to synchronize multiple loops with each other. So one use case is synchronizing acquisition and processing loops. Another one is synchronizing execution between multiple FPGA loops. You can also synchronize tasks to a common signal, for example, like a sample clock or a clock coming from somewhere else, like an external clock. And also synchronizing I/O from different C-Series modules. So we'll talk about each of these bullets in more detail. So let's say we want to synchronize the acquisition and processing loops. Well, in the previous lesson, we talked about a way to do that. So in this case, we're going to be using FIFOs. So if you think about it, if you look at that top loop and the bottom loop, the top loop is acquiring data and the bottom loop is processing it. So by using a FIFO, we've actually kind of synchronized these loops. The top one is just going to be acquiring every 100 ticks or milliseconds or microseconds, however that's configured in the loop timer. And the bottom loop is synchronized with it. The bottom loop is going to read something from that FIFO as long as something is available to read in the FIFO. Okay, so the bottom loop is pretty much synchronized with the FIFO. Sometimes you might need to synchronize the execution of code in multiple loops. And one way we can do that is using occurrences. Okay, so let's take a look at this example on the block diagram. So on the block diagram, first we're going to use the generate occurrence function, and then we're going to pass that reference of that occurrence to the top loop and the bottom loop. Okay, so in the top loop, what's going on is we're executing some code, and then if that code meets some sort of condition and outputs a true for that condition, then we're going to go ahead and set that occurrence. Okay, and what that will do is it'll trigger that bottom loop. So notice that in red on the bottom loop you see wait on occurrence. Okay, that wait on occurrence is just going to wait for something to set the occurrence. Once that occurrence has been set, the bottom loop in parallel is going to go ahead and execute some code that's associated with that occurrence. Okay, so if you think about it, we've got this bottom loop that's running in parallel. Every single time some condition happened, we did a set occurrence, and that bottom loop is going to execute some code that corresponds to that. Okay, so by using occurrences, you can see how we can synchronize the execution of parallel loops here. Okay, on this slide we see another example of using occurrences. So let's take a look at some actual code. Again, we're going to first do a generate occurrence, and we're going to pass that reference into both of these loops. Okay, so at the top loop, we see we have the top loop executing with a period of 10 on that loop timer. And then inside the code, we see that we're acquiring from some analog inputs and doing some processing on that. And then every time that happens, we're going to, every single time that the analog input processing is finished, it'll immediately set that occurrence. So if you look at that bottom loop, in parallel, every time that set occurrence happens, it's going to execute some logic. So in this case, every time the set occurrence has been set, we're going to go ahead and make the digital line to true. And then we're going to wait a pulse width, and then we're going to set that digital output line back to false. Okay, so pretty much every time we finish processing that analog input, we're going to output a pulse with a specified pulse width. And that's happening in parallel at the same time as that acquisition loop on top. Okay, so this is just another example, and hopefully that'll help you think of things that you might want to do in your application. Okay, so now we're going to do a demonstration of occurrences in LabVIEW, and we're going to synchronize the execution of code in multiple FPGA loops. Okay, so let's go into LabVIEW. Okay, so now that we're in LabVIEW, if you want, you can follow along. This project and VI is found in the exercises demonstrations folder. So I'm going to open up the occurrences VI right here, which we see right over here. And let's go ahead and look at the block diagram. Okay, so I'm going to rearrange this so you can see the block diagram and front panel at the same time. So notice here we've got generate occurrence, okay, and this reference is getting passed into 3 loops. Okay, so over here, this loop is going to set it. Okay, so if the set occurrence control is false, nothing is going to happen. but if I set it to true, then it's going to set this occurrence. And then if we look at these bottom two loops, both of these two loops are waiting on occurrence. Okay, so by setting the occurrence up here, it's going to trigger something to happen in this loop and also this bottom loop. Okay, so you can actually have multiple loops waiting on the same occurrence. So the code here that we have here is just more of a proof of concept. All we're going to do is we're going to toggle that LED. Okay, so we're going to turn it on or off. Okay, so let's go ahead and run this. And let's take a look at this proof of concept. So if I was to set the occurrence, notice that both of these loops down here were able to see the occurrence, and they both executed some code that was synchronized with that occurrence. Okay, so if I press it again, notice that it toggles them both off. So as you can see right now, both of those bottom loops are synchronized with that top loop using an occurrence. Now you can synchronize FPGA loops using occurrences. Next, we will synchronize FPGA loops by sharing a common signal. In the previous section, we synchronized FPGA loops using occurrences. By the end of this module, you will be able to synchronize FPGA loops by sharing a common signal. So let's talk about another way of synchronizing FPGA loops. This method that we describe will be sharing a common signal. So another way you can synchronize execution between multiple FPGA loops is by generating and sharing a common signal. So the first thing you would need to do is you would need to generate a Boolean signal to provide synchronization among FPGA loops. So if we look at the bottom block diagram here, we have a loop here that is generating a clock signal. So if you take a look at this, we have a loop timer there, and we also have a generated clock. Okay, so that clock is basically toggling between true and false. Okay. The next thing you would need to do is you would need to trigger execution in other FPGA loops by monitoring the value of that Boolean signal. Okay, so notice that the name of this signal right now is generated clock. So if we were able to monitor the value of generated clock in other loops, we can synchronize something with that clock. So on this slide, this is kind of an extension of the previous slide. So in the previous slide, we were generating a clock. In this slide, we're monitoring that same clock signal. Okay, and in this case, we're looking for a rising edge, and we're trying to synchronize some code to happen every time a rising edge happens. So let's take a look at the code. So in this loop, we see in the first part, we're waiting for a trigger. Okay, so notice we have a single cycle time loop, so it's going to be checking for that signal very quickly. And we're looking at the generated clock signal. And notice with that logic there, all this is really doing is it's looking for the previous iteration to have a false value and the current iteration to have a true value. That represents a rising edge because it's going from a low voltage to a high voltage. So once that happens, it's going to exit that single cycle time loop and then go to the next frame and execute the code that is associated with that trigger. So pretty much what happens is this is going to wait for a rising edge, and once that rising edge happens, it's going to immediately execute some code that you want to happen every time there's a rising edge. Okay? And once that code has been triggered, it's going to go ahead and wait again for the next rising edge. So here, this is a very similar loop, except instead of looking for a rising edge, it's looking for a falling edge. So if we look at the code here, let's look at the section where it's waiting for a trigger. All this code is really doing, notice that the greater than function has been replaced with a less than function. What we're looking for here is a previous iteration of true and a current iteration of false. Okay, so that represents a high voltage going down to a low voltage, in other words, a falling edge. Okay, so once that falling edge occurs, notice that we'll exit out of that single cycle time loop, and then we'll execute the triggered code. On this slide, we see an example of some code that is looking for an analog trigger. Okay, so if we take a look at this code here, so the first part in that single cycle time loop, what we're looking for is we're looking at the analog input value, and then we're seeing if it's greater than that threshold. Okay, so what we're looking for here is essentially the previous iteration had a value that was not over the threshold yet, and then the current iteration does have a value that's over that threshold. So really what this is doing is it's looking for a time where that analog value crossed over from under the threshold to over the threshold. And once that happens, we're going to exit that single cycle time loop, and we're going to execute some code that's associated with it. So if we look at this particular example, every time that analog edge gets triggered, we're going to set over threshold to true for our indicator, and we're also going to output a true to our digital output line. So in this slide, we see an example of a block diagram that is one, generating a clock at the top, and then those bottom two loops are monitoring the rising edge of that clock and the falling edge of that clock. And the code for those rising edges and falling edges are going to be synchronized with those rising edges and falling edges. So this slide is pretty similar as well, except instead of generating our own clock, what we're doing is we're sharing an external clock. So if we look at the very top loop there, notice that we are reading from a digital input line, and that is going to represent our clock that we're pulling in externally. Okay? And now we have some code. So the code in our middle and bottom loops, those are going to synchronize code to rising edges and falling edges of that external clock. Okay, so now that we've seen this code in our slides, let's go ahead and open it up in LabVIEW and see what it looks like. Okay, let's take a look at this demo. Feel free to follow along in your own computers if you want. This is in exercises and demonstrations. So let's go ahead and look at the share Boolean signal VI. So let's go ahead and look at the block diagram here. So this is the block diagram that you saw in the slides. So we are generating our own clock, and we're synchronizing some code to execute on every rising edge and every falling edge. Okay, so every rising edge is going to make the rising edge trigger LED turn on and off, or toggle. And then every falling edge is going to make the falling edge trigger LED toggle on and off. Okay, so let's take a look at the behavior. So notice that generated clock, I have an indicator right there, and that's going to show us what the current state of this clock is. And we're going to make a clock that's running pretty slow so we can see what's happening. Notice that it's going to toggle the clock every 2 seconds here. So let's go ahead and run this and see what happens. So notice there's a rising edge, and when this turns off, that's a falling edge. When it turns back on, it's a rising edge. When it turns back off, it's a falling edge. So you can take a look at this for a little bit longer, and you'll see that every time there's a rising edge on that clock, it'll synchronize execution with the rising edge. And every time there's a falling edge on that clock, we'll synchronize some logic here with that falling edge. Okay? So let me go ahead and stop this. And close this. Let's go to sharing an external clock. So if we look at the block diagram, again, it's going to be very similar, except the thing that we've changed here is we're sharing an external clock. So we have on connector 0, digital input line 0. We're going to monitor that, and that's going to be our clock. So, so theoretically, we have a clock that's wired up to that particular input. Okay. In this case, we don't actually have a R series board. We're actually simulating it. So since we're simulating on it on our development computer, we're just going to get some random values for our clock. Okay, so if I run this, it probably won't make too much sense. So notice that these are just simulated values. It's happening way too quick for us to really kind of see the synchronization. But as you can see, with the falling and rising edges of this clock, it's going to trigger things that happen and synchronize the code over here. Okay. So I'm going to go ahead and stop this, and that's it for our demo. Now you can synchronize FPGA loops by sharing a common signal. Next, we will synchronize on-demand C-series modules. In the previous section, we synchronized FPGA loops by sharing a common signal. By the end of this module, you will be able to synchronize on-demand C-series modules. Okay, so let's talk about the need to synchronize I/O, specifically C-series modules for CompactRIO. So some applications are going to require a high level of synchronization between channels. For example, if you're taking several vibration or sound measurements from multiple channels, or you're doing multiple types of measurements, and you want to make sure that all those measurements are happening at the same time. So in this section, we'll talk about how you would do that. Okay, so first, let's talk about synchronizing on-demand C-series modules. And the way that we're defining an on-demand module in this slide is it's modules that use the loop timer VI to time their loop rate. Okay, so on the slide you see some examples of on-demand modules. So for example, digital modules are going to be on-demand modules. Also, analog modules with a SAR, that stands for Successive Approximation Register, ADCs, which stands for Analog to Digital Converter. Okay, if you want to see the type of ADC that an analog C-series module uses, you can look in its specifications. So an example of that is the 9215 or the 9263. Another example of an on-demand module is multiplex modules, so 9211 and 9207. So at the bottom of the slide, you see that with these modules, the way that you time them is with a loop timer VI. And then you would put an FPGA I/O node in the next frame. So the way that you would synchronize on-demand C-series modules is you would place all the channel reads and updates in the same I/O node. So if you take a look at this block diagram, you can see that in the while loop, we've got the loop timer to time our while loop. And then we see that all of our I/O that we want to synchronize are going to be placed in the same FPGA I/O node. Okay, so you can mix analog input, analog output, and DIO channels with minimal skew. So just one thing to keep in mind, the maximum loop rate possible is limited by the slowest channel in that FPGA I/O node. So think about the different channels that you have in there. If you have a digital channel, you know that's going to execute within one clock tick. Analog channels, again, are going to require multiple clock ticks usually, right? So analog input is going to require several clock ticks. Also, if you have a multiplex module, then each additional channel that's in there, because it's multiplex, is going to require some additional clock ticks. Now you can synchronize on-demand C-series modules. Next, we will synchronize delta sigma C-series modules. In the previous section, we synchronized delta sigma C-series modules. By the end of this module, you will be able to synchronize delta sigma and on-demand C-series modules. Okay, so let's say we have delta sigma modules and also on-demand modules, and we want to make sure that those are synchronized together. Well, on this slide, we see how we're able to do that. So if this is the case for you, then what you want to do is first, you want to design your application for delta sigma module timing using data rate property nodes. So if we take a look at this, the first thing you would do is you would design it this way. So you go to the first frame and you're going to do the data rate, set that up, and then you're going to go to the second frame and start your module. And then in the third frame, notice that that while loop is going to be timed by your delta sigma module, right? So the while loop is going to execute at the same rate that you defined by data rate in that first frame. Okay? Once you've done that, then your second step is you're going to add your on-demand I/O modules separately. Okay? So now notice that in that while loop over there, you've got your on-demand modules. And because that while loop is being timed by the data rate associated with your delta sigma module, those on-demand modules will also be acquiring data at that same rate because it's in the same while loop. Now you can synchronize delta sigma and on-demand C-series modules. Next, we will describe the basics of using sub-VIs in LabVIEW.